So last week we had about 3 or 2 presentations on physics, so I thought, one more wouldn't hurt. So today I'm doing mine on the electrostatic force and electric fields. Now I could have called this charge, this presentation, but we all have some intuition about charge that's usually wrong. An example of this is last week I was talking to my friend who's training to be a chef about capacitors. What these are 2 metal plates that you connect to a battery, and it charges them up. They hold charge. So I asked him what would happen if you took the battery off, and he said, would the charge just go away? I said, no, why would it? People seem to think that charge is like a liquid that kind of like flows, in and out of stuff. But we also know that everything's made up of particles. So those 2 ideas don't really go together. Everything is made up of particles, so charge is just a property of those particles. And particles are nice. We know how to deal with particles. The 3 laws that govern particles are Newton's laws of motion. Everyone knows these in some form. A body at rest stays at rest unless moved by an outside force. The direction of an object's motion is in the direction of the force impressed. But the last one is the one that we're going to focus on today. And that's that to every action, there's always an equal and opposite reaction. Now, this is an important idea. If everyone right now wants to push on their desk, you can feel that the desk kind of pushes back, and that force backwards is the same force that you push on your desk. This occurs with every force. So if you have 2 charged particles, say one with a charge of 5 and one with a charge of 1, the force on both is exactly the same in opposite directions. At first, this sounds kind of counterintuitive, but we're kind of lucky that it's that way, because it makes everything work the way it should. Otherwise, you get weird stuff happening. Like you can make cars by having a large magnet and a small magnet, and have the large magnet kind of pull it one way. The reason this doesn't work is because of this 3rd law. So we can actually use this right now to start finding the equation for the force that charged particles exert on each other. We start by putting F equals K. K is a constant of proportionality, which has to do with our choice of units, because the meter, the gram, the foot, the mile, the pound, everything, that's all arbitrary. That's just us. So this kind of converts it into actual units that has to do with basic constants, like the unit of charge. An electron has a charge of 1 and a proton does too. So what Newton's 3rd law says is that the force on both particles is proportional to both charges, which we call Q. So this is the force that's on both particles that are interacting, but they're in opposite directions. So there's actually only one more part here that we have to deal with, and that's distance. We know that if you have 2 charged particles, we could use magnets, I guess, for an analogy. The force on them falls off as they get farther and goes up when they get closer. It was discovered through experiment that if you have a certain force at a certain distance, if you doubled that distance, the force would fall off by a factor of 4. If you tripled it, it would fall off by a factor of 9. This is known as an inverse square law, and it pops up all over in physics. This actually looks almost exactly alike to Newton's law for gravity, only these 2 charges are replaced by mass, but it's the exact same other than that. So this law is a very important law. So that's fine. I mean, this is the law that governs forces between charges. But it presents a deeper philosophical question, which is, how does this charge know that that charge is there to move that way? There's a distance between them, and that's kind of weird. It's as if you had a blind, deaf, mute guy in a room, and he knew when someone else walked in. It's weird. You wouldn't expect that. And the short answer to that is that they don't. They actually interact through a thing called the electric field, which looks like this. And at first you might think that this is like a mathematical construct, but it's a real thing. These lines kind of act like flexible tubes or like jump ropes. So if this one moves, it kind of sends a wave out. It's like playing Snake with the other charge. So it sends a wave out, and the other one feels that wave, and it moves, whatever way. If they're negative, it kind of pulls it, kind of like moves backwards. And if it's positive, it kind of sends it. And the proof that these fields actually exist is that that information travels at a certain speed. And that speed is the speed of light, and that's important. So that's pretty much it. That's how charges interact. And this is why they do it. This is how they know that the other charges are there. And that's fine, but You know, I could leave you guys with that, but I thought I'd leave you guys with a question. This is an atom. We all know what an atom looks like. This is actually a nitrogen atom. So we have the nucleus here in the center. It's actually a lot smaller. Like the nucleus in an atom would be like if you had a marble. Then the orbit of the electrons would be the size of a football stadium. So this is off scale. But this is a nitrogen atom. So we have the electrons here and the protons here. Now each proton we know has a charge of +1. That's known. The distances between each proton is on the order of a femtometer, which is 10 to the negative 15 meters. So this is a trillionth of a millimeter. It's a small distance. So we know from our equation earlier, here, I'll bring it back up, that it's inversely proportional to the square root of distance. So if you divide by a small distance and square it, you get a really huge number here. So this means that between each proton, there's a really huge force because they're so close. And what's interesting is this force is on the order of about 15 pounds. These are small particles. So you have a force of 15 pounds on each proton kind of throwing it out. So the question is, why doesn't the atom fly apart? And it took some time to figure it out, but I'm not going to go into that. I'll leave that for you guys. That's it. Thanks.
All right, so Vincent, you're up.
I thought that was a very well rehearsed speech. You were very clear in making your 3 points. You spelled it out on your PowerPoint. At the beginning, you spelled out your 3 points in. I like that analogy with the blind guy. It was something like people can relate to because it's not physics related, it's more abstract. And you did a good job explaining that equation. And overall, it was a good speech. Yeah.
All right, I'm going to start with the things I liked about the presentation. You do a very nice job speaking to the audience. You are confident, you project well, you seem to know the material well, so you're relaxed while you're speaking to the audience, and so we're not going to have any problems that way. I also like the visuals for the most part. The images and the Newtonian principles I thought were fine. However, whenever you start putting math equations up, I feel minds clicking off. You know, it's like, I'm sorry, you know, this is the wrong situation, and that's the biggest problem I have with the speech, is that there's not enough audience analysis here. You have to think about, what does this group need to know about this subject? How is it going to be applicable or useful to them? If we were in if we were in your physics class, or we were in an electronics class, and you were putting this, and this was in the context of a discussion that you were having about some subject. Please don't stand there. It's kind of creeping me out. Have a seat. You know. I don't like people to feel like they're a target. You know, it's bad enough when I'm making comments. You know, people feel like, oh, he's ragging on me. But when you stand up there, it's like the little kid in front of the classroom. And I don't want you to feel that way. You know. Yeah, kind of like that, and I don't want anybody to feel that way. So it's better to sit down. I don't want to feel like I'm putting you down, because I don't think I am. But it's just the context for a general audience like this who don't have a specific need for this information it's a waste of time. Can anybody remember the equations that you just heard? Could you perform those functions? Yeah, I'll bet all those people who've taken a physics class would be fine on that, you know. Everybody else is going, yeah, you know. It's like, and if you, I liked, like Vincent said, the example about the blind, deaf, mute guy, you know, okay, I can kind of understand an application that's going on there. And I like the opening story that you had about your friend who is the chef, and you're talking about that. I can kind of see okay, there's a way to kind of relate to it there. But outside of those two contexts, mostly it just sounds like it's abstract. We're not looking at anything in particular. We don't have we don't have any way to apply this for ourselves. Is it important for us to understand in a larger context? It probably is, but you're starting at a point that's too far in for a general audience, and your focus is too narrow for the general audience. And so I think that's the problem. I didn't think it was well organized. I thought that the visuals give it a little bit of structure, but it seems to me that from an oral perspective, it's bullet point stuff. We're getting and here's the equation, and here's the principle, and here's this other thing, and it's whoa, let's group this material together so that we can see how these pieces fit with one another and gives us a whole picture. I'm still not sure I know what the thesis or the specific purpose of the speech is. I know what the topic area is, and it just feels like I'm wandering a little bit trying to figure out where I'm going with this. It's not that the topic is bad, but I think it's just you've taken it in a direction that doesn't work for a general audience here. And if everybody else understands it, that's fine. But you know what? I'm in your audience too, and I don't understand it. I mean, all those equations, I'm looking at them going, why am I listening to equations at 10 o'clock in the morning about something that I'm sure is important, but I need to know why it's important and how it's important and put it into some real-world application that makes sense to me when this is not the subject matter that I am versatile in. And I think that's the biggest problem here. I'm sure the math is all fine. The comparisons that you make within the Newtonian principles, they all make perfect sense, and I think you're right. Everybody has a passing familiarity with those sorts of things, so you're in good shape there. But when I'm looking at F equals K, and then it's 15 pounds, and I'm like, what the heck? And then when you add this, and you've got, and you cube this and square that, and huh? Slow down. It's too much to do in a short amount of time without enough context. That's the big problem. All right, thank you.